Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our investigation of amino acids and are going to focus on the acid-base properties of said acids. Now, last lecture, we indicated that amino acids are less acidic than most carboxylic acids and less basic than most amines. They also have relatively high melting points, usually greater than 200 degrees Celsius, and they're very soluble in water, much more soluble in polar solvents like water than in nonpolar solvents. The properties are typical of ionic substances. They suggest that amino acids undergo an internal acid-base reaction, and I indicated that such amino acids do have the equilibrium shifted to the right because the carboxylic acid is a stronger acid than the protonated amine. So this equilibrium shifts this way, and indeed we produce an ionic species. Now, overall, the molecule is still neutral. But the result is the dipolar ion you see. These are referred to as inner salts, or sometimes they're called Zwitterions. A Zwitterion is a dipolar ion in which the molecule has a minus and positive charge. There's charge separation in the molecule. In its Zwitterionic form, the amino acid can act both as a base or an acid. Because of that, it's amphoteric. The term amphoteric or ampholyte simply means it can act both as an acid or base. Now, other molecules that are amphoteric, one most familiar to you would be water. Water can pick up a proton and become H3O+, or it can give up a proton and become hydroxide. While the overall neutral Zwitterion of an amino acid can do the same thing. If we start with the Zwitterion, if we react it with acid, the Zwitterion can act as a base. It can grab the proton, in which case you would have R, CH, C double bond OH, NH3 plus. And we'd end up getting the protonated carboxylic acid. We'd get a cation forming. The Zwitterion is overall neutral. Now, if we throw in base, the Zwitterion can act as an acid, donating a proton from the NH3+, and then we get this. And it has lone pair there. Right. And this is an anion. Hence, an amino acid can exist in three states. It can exist as a Zwitterion, or it can exist, which is overall neutral. It can exist as the anion, where it is a negative ion, or it can exist as a cation, where it has a positive charge. Now, the form that the amino acid actually exists in at any given time is dependent on the pH of the solution. At extremely low pH, extremely acidic solutions, you will form the cation. The molecule will be fully protonated. For all amino acids, proton loss from the cationic species can be described by two equilibrium constants, Ka1 and Ka2. If I replace this arrow, there is an equilibrium between the cation and the Zwitterion, and that equilibrium is given by a constant Ka1. Likewise, the Zwitterion can convert to the anion, and there is a second equilibrium constant to describe that equilibrium, Ka2. For a neutral amino acid, Ka1 refers to the dissociation of the strongest acid group. When we're fully protonated, we could ask the question, where does the proton come from? Well, if we're comparing the NH3 plus versus CO2H, the first one to lose the proton is the stronger acid of the two functional groups, and that turns out to be the carboxylic acid. So Ka1 describes the loss of a proton from CO2H. Ka2 describes the loss of a proton from the less acidic NH3 plus. Okay, so we can set up a description, if you like, or a calculation for each Ka value. And let us do that now. Let's consider the fully protonated form, and let's take one of the most simplest of amino acids, glycine, where the H group, or the R group, is an H. Okay, now I'm going to take this molecule and let's say we dissolve the fully protonated form in water. We have protonation, H3O plus, and then we get our Zwitterion, H3N plus, CH2, CO2 minus. Now, remember, an equilibrium constant, K, equals the concentrations, the product of the concentrations of the products. So I take concentration H3O plus times the concentration of the Zwitterion. We divide that by the product of the concentration of the reagents. And so we've got concentration H2O times concentration of the cation. Now, remember, water is a solvent, and in essence, it's present in vast excess. So the little bit of water required to produce H3O plus doesn't affect the total concentration of water. And because water is a constant, we can multiply both sides by the concentration of water. If we do that, water concentration cancels here. And so we can remove it from our equation. So we have two constants, an equilibrium constant times the concentration of water. This was defined last semester as Ka. So inherently, Ka has the concentration of water built into it. Now, Ka for this equilibrium is defined as Ka1. And initially, at very low pH, we have approximately 100% of the fully protonated. However, as we titrate, when we reach the first half equivalence point, the concentrations of the cation and the Zwitterion become equal. Now, you'll notice at half equivalence, if we were doing a titration, the concentration of the Zwitterion will equal the concentration. When that happens at half equivalence, these two will cancel. And when they cancel, Ka1 at the half equivalence will equal the concentration of H3O plus. And since that's the case, the negative logs of both sides will be equivalent. And the negative log of the concentration of H3O plus, remember, is just pH. And the negative log of Ka1 is what we call pKa1. Now for the molecule glycine, this turns out to be a value of 2.35. It will vary slightly depending on the tabulated data you use. Now we can go through the same type of calculation, exactly same calculation for Ka2, except in this case we're starting with the Zwitterion. Reacting it in water, and we get H3O plus, and we get the anionic deprotonated form, fully deprotonated. Now, if we set up the same equation as we did above, Ka2 can be found, and it will equal the concentration of H3O plus times the concentration of the Zwitterion all divided by the concentration of the anion. Remember, Ka has the water concentration built into it. Now remember, at the half equivalence point again, pKa2 will equal pH, because the concentrations of these two will become equal at a half equivalence point. Remember what the half equivalence point is. You titrate and you're slowly removing the Zwitterion and producing the anion in this case. Eventually these two concentrations are going to become equal. When you've titrated half of the Zwitterion, when they become equal, they cancel. And so Ka2 equals concentration of acid, or pKa2 equals pH. And for that, pKa2, if you do a calculation, is 9.78. All right. Now, let's consider this a little more carefully. At the first half equivalence point, the concentration of the fully protonated form and Zwitterion are equal. Okay. At the second half equivalent points, the concentration of the Zwitterion and anion are equal. Right. What would happen if I went 1/2 the distance between both of these values? 1/2 the distance between 2.35 and 9.78. 2.35, the concentration of the protonated form and the Zwitterion are equal to each other. At 9.78, the concentration of the Zwitterion and the NH2CH2CO2 minus are equal to each other. Halfway between those two numbers, the fully protonated form will have converted to as much Zwitterion as it can, and the Zwitterion will have not started to go to the anion very much. Let's try to make a graph in which we can picture this. What I'm going to do is create a titration curve for you, if I can. Now this titration curve will consist of pH values, and so we'll go up 2, 4, 6, 8, 10, and 12. Now, the bottom scale, so this is pH, the bottom scale is going to be measured in equivalents. Okay, equivalents of hydroxide. So I'm going to put EQ of OH minus. And we're going to mark 0.5, 1.0, and let's put 1. Try to make it the same distance. 1.5. Now, what's going to happen is at the half equivalence point, this is where pKa1 occurred. Okay? And remember at pKa1, the concentration of the fully protonated acid form, and for glycine that equaled 2.35. The concentration of the fully protonated form and concentration of the Zwitterion were equal. Then at the second half equivalence point, we got pKa2. pK2, the concentration of the Zwitterion and the concentration of the anion will equal. Well, halfway between these two values, we arrive at the first equivalence point. Now, what species is going to exist at the first equivalence point? Well, if the concentration over here of the protonated form of Zwitterion are equal, the concentration over here of the Zwitterion and anion are equal, as we go back towards this point, the concentration of the Zwitterion keeps increasing until you get to this point. And so the first equivalence point is the point at which the Zwitterion is the primary thing in solution. Now you're familiar with this with water. Consider water for a second. Water can exist in two forms. It can exist in the fully protonated form, H3O+, and it can exist as hydroxide. And you always have hydroxide and H3O+ present in trace amounts. But at what pH do you mainly have water? Well, water exists as H2O primarily at a pH of 7. The concentration of H2O is greatest at a pH of 7. That doesn't mean there's no H3O+, and that doesn't mean there's no AOH-. In fact, that's where we get KW from. The concentration of H3O+ and concentration of hydroxide is very, very tiny, 1 times 10 to the minus 7. Okay. But water exists at a pH of 7 as its major form. The Zwitterion will exist just like water does at the full equivalence point in major form, and both the anion and cation will be present in only trace amounts. But this pH will occur at 1/2 the distance between 2.35 and 9.78. Now, since this pH right here is the pH at which the Zwitterion predominates, and since the Zwitterion is a dipolar ion, which is overall neutral, that means the solution becomes overall neutral, with no cations or anions in it. Hence, it only has the Zwitterion, which overall is neutral. We call this the isoelectric point. The pH at which the Zwitterion exists exclusively is called the isoelectric point. And instead of calling it pH, the pH at which this occurs, it's often called PI for isoelectric. And PI will equal 0.5 times pKa1 plus pKa2. Okay. So if you solve this for glycine, you take 0.5 times 2.35 plus 9.78. You solve that, you'll get approximately 6.07. Okay. Now what's interesting is this is the typical isoelectric point of a neutral amino acid. Why do I say neutral? Well, let's take a look. A little more closely. at glycine. Glycine, remember, had as an R group the H. The R group H is attached to a carbon. So this carbon, this group, the R group, is neither acidic nor basic. It's a neutral side chain, and so it's a neutral amino acid. And it turns out amino acids that have side chains that are neutral have pKa's somewhere around 6. Okay? Maybe as low as 5 at the lowest. What happens, though, if we change this side chain? Well, let's consider that. First, I want to redraw the equilibrium for glycine, if I can. Okay, so let's try that. I'm going to take the fully protonated form, and I'm going to show the side chain as an H. And I'm going to draw the equilibrium, titrate with base, and you'll find pKa1 equal 2.35. That gave me the Zwitterion. Which, if I titrated with base, would go right through to the fully deprotonated form and generate the anion. CO2 minus. That should have been a minus. There we go, and pKa2 equaled 9.78. I believe that was correct. Yes. Okay. This happens in the case where the side chain is neither acidic or basic. But let's consider the exact same situation as previous. As in the glycine case, if all of a sudden we put an acidic group on the side chain. Let's consider, for example, glutamic acid. So let's put an acidic side chain. Well, if we have an acidic side chain, for example, like in glutamic acid, and we start with the fully protonated form, we have a CH2, CH2, a CO2H. Now if we titrate with base, we have 3 proton sources. The question now becomes, which, if you like, which CO2H loses its proton first? Well, if we think of it this way, the NH3 plus is very electron withdrawing. Nitrogen's very electron withdrawing. If I pull an H off either CO2, I'm going to get a CO2 minus. That CO2 minus, right, is going to be stabilized by resonance between the two oxygens, and there's no difference between them. However, having the CO2 minus closest to the NH3 plus, the NH3 plus acts like an electronegative group and will stabilize the negative charge that is closest to it. Because of this, the CO2 minus that forms closer to the NH3 plus will be more stabilized. Hence, the CO2H that's closest to the NH3 plus becomes more acidic. So it is this one that's lost first, and we create our Zwitterion. Now the pKa, or half equivalence point, for this equals 2.10. Now if we continue to titrate with base, what will deprotonate next? Well, CO2H, carboxylic acid, is a stronger acid than NH3 plus. So this CO2 minus, the second CO2 minus, will dissociate and we'll get NH3 plus. CHCO2 minus. CH2, CH2, CO2 minus. Now, notice that we went from, a cation plus 1 to a charge of 0, and now we're at a charge of minus 1. This pKa2 for the anion formation, we have pKa2, it has a value of 4.07. Now as I write down these numbers of pKa values, you may immediately start thinking, well, how does he get these numbers? Don't panic about the numbers. You can't get them unless you do the titration experiment. So clearly the pKa numbers I'd have to give you. All right. But the interesting thing is we're not done. Because there was a third group to deprotonate, we can do one more equilibrium, and unfortunately I'm going to have to turn it this way. So if we add one more hydroxide, we can deprotonate the NH3 plus. If we do that, we get NH2, CO2 minus. We've got CH2, CH2, and a CO2 minus. Now, what's the charge on this molecule? It's -2. We've got a dianion. This, right here, is a third pKa. We have a pKa3. What's pKa3 equal to? Well, it's equal to 9.47. pKa3, 9.47. All right. So we've got structures. I'm going to label them. A is a cation. B is neutral. C is -1, and D that's -2. Okay. Working with glutamic acid. I need to know the structure of glutamic acid, and I need to be able to draw this type of equilibrium for glutamic acid. I need to be able to insert the pKa values, and I've got to know which group, which CO2H, which NH3 plus deprotonates first. This type of equilibrium has some information that we can use when we've labeled the pKa values for it. We can determine the pH at which the Zwitterion structure B predominates. You might say, well, the formula is 1/2 pKa1 plus pKa2, but here we have 3 pKa values. Which one do we use? We use the 2 pKa values that surround the Zwitterion, the neutral species. Now you say, well, the Zwitterion is not neutral. It has cation negative charge, but overall it's neutral. So clearly, in this case, the Pi equals 1/2 pKa1 plus pKa2. And the reason for this, of course, is those are the pKa values that surround the Zwitterion. So we take 1/2 pKa1 plus pKa2, which in this case is 2.10 plus 4.07. If we add that together, we get 6.17. If we solve for that, we get the Pi isoelectric point. Pi equals 3.08. This isoelectric point value is much lower in pH than a neutral amino acids isoelectric point value. In fact, most acidic, all acidic side chains have isoelectric points somewhere around 3. So you're a neutral amino acid if your isoelectric point is around 6. Okay? 6 to 7, maybe 5 at the lowest. And your isoelectric point around 3, you're an acidic amino acid. But these equilibriums also give you more information than just that. Remember, if I could give you fixed pH values, you could tell me who's the predominant species in solution. For example, in this structure, if I gave you a pH value of 1, at a pH value of 1, the species that predominates, that has highest concentration, is the concentration of structure A. A predominates. Why? I know that because of pKa1. pKa1 is 2.1. Remember, that's the half equivalence. That's the point at which the concentration of A equals the concentration of B. So if we're less than 2.1, A is greatest. If we're at, say, 2.5, then the concentration of B is the greatest. Because at 2.1, the two are equal. What if I pick a pH of 4.07? If I give you the exact pKa value as your pH, you would say the concentration of B equals the concentration of C, or B equals C. And if I picked a pH, say, of 10, well, since pKa3 is 9.47, D must be major. So given any kind of value for pH, you could tell me who's the major species in solution. Also, be careful. I mean, if you looked at pKa 4.07 or pKa 9.47, remember to say that the concentrations are equal when you're given pHs that are identical to pKa values. All right. Let's take a last look at a basic side chain. Basic side chain produces what we call a basic amino acid. A nice example of this is the molecule lysine. Let's start writing the same equilibrium we did previously. Lysine has 4 CH2 groups, and attached to that is an NH2. And I'm going to protonate all the groups. And so we start with a dication, a +2 charged molecule. And pKa1, reaction with base, we throw in hydroxide, would deprotonate the most acidic group. And the most acidic group, of course, is the CO2H. And if we draw that, there's only one CO2H, so that's pretty easy. And that produces a cation, a +1 charged species. And the pKa1 for that is 2.18. Now, I can label this molecule A and this molecule B. No problem. Now we've got two NH3 pluses, and we have to decide which one is going to deprotonate first. And this is a bit tricky. See, we have a CO2 minus group here, which is electron rich. And one might think that the CO2 minus would help stabilize the NH3 plus. That is, this is electronegative, it's closer to a CO2 minus, electron withdrawing effects would help stabilize the positive charge. But we have enough carbons in this 4-carbon chain for the NH3 plus to wrap around and actually hydrogen bond to the CO2 minus. Though I'm not showing it, we could wrap this around and get the hydrogens in interaction, and through hydrogen bonding, stabilize this NH3 plus more. And though you wouldn't have predicted it, you now are told and are expected to remember that it is this one that deprotonates first. Leaving the NH3 plus on the long chain. Four CH2s and then the NH3 plus. And you'll notice this is a Zwitterion. So this has neutral charge, C. Again, we titrated with base, and this gives us pKa2. And our pKa2 value equals 8.95. Okay, the last equilibrium. Reaction with hydroxide will deprotonate the NH3 plus. Generating an anion, which we'll label as D. And the pKa3, put it here, pKa3 equals 10.53. That goes right there. So I could draw four structures. So just like the acidic side chain, the basic side chain gives you another group that can be deprotonated, and because of that, there are three pKa values. Once again, we can ask the question, which pKa values do I use to determine the isoelectric point? The answer to that is, remember, the isoelectric point is the point at which the Zwitterion predominates. The Zwitterion is the dipolar ion that overall has neutral charge, and that's structure C. And therefore I pick the pKa values that surround structure C. And so in this case, Pi equals 1/2 pKa2 plus pKa3. And if you solve this, you get 0.5 of 8.95 plus 10.53. And you end up with an isoelectric point value of 9.74. Okay. So for basic amino acids, or amino acids with basic side chains, the isoelectric point is in the range of 7.5 to 10. Once again, given any pH, I could ask you to identify the major species in solution. If I give you a pH of, say, 8.95, you would say the concentration of B equals the concentration of C, because at the half equivalence point, the two concentrations are equal, and pKa values are found at the half equivalence point. If I gave you a pH of 12, you would say concentration of D is major. So you can identify which groups. Note, to reiterate one last time, for a neutral amino acid, the isoelectric point is usually between 5 and about 6.3. In fact, let's write this down. So, a neutral amino acid okay, and we'll just put Pi at the top here. A neutral amino acid has an isoelectric point value of between 5.0 to 6.3. An acidic amino acid the isoelectric point is approximately 3. And for a basic amino acid, our isoelectric points range from about 7.5 up to about 10. All right. Now, next lecture, we're going to actually look at some pKa values. And we're going to examine in the next Scribblecast various pKa values. These would be given to you on a test, but if you're given a chart of pKa values, how do you determine which group is deprotonated? So we'll be discussing that, as well as we'll be revisiting our 20 major important amino acids found in proteins, biologically important amino acids, and we'll be revisiting them and determining which ones are acidic amino acids, which ones are basic, and which ones are neutral. After which we'll start moving on to the polymerization of amino acids into peptides and proteins. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.